So in this video, I'll be talking about affine maps and affine spaces. So basically, let's start with affine space first. To define affine space, French mathematician Marshall Berger says, an affine space is nothing more than a vector space whose origin we try to forget about by adding translation to the linear maps. So let's just think about the origin that we try to forget about part. So what he is basically saying is that affine space is a like a vector space without origin. So let's say when we actually talk about a space, so let's take this R2 vector space. So this space actually comes with the choice of origin, which is a very distinguished point in this space in such a way that even if you apply a linear transformation, the origin won't change, and all the vectors and the lines that go by are actually passes through origin. But the point is that why do we need to have this construct of origin in the here? So, oops, yeah. So basically, we could have something which is equally linear, but which doesn't pass through origin, right? So what origin means is that it's like just a perspective. So we could see like this both of these lines are sort of parallel, but one is not passing to the origin, another is. So that is like a different perspective. And the thing is that like you might have dealt with such sort of affine lines in maybe high school geometry, but like at that time we didn't think much about it. And in this particular sense, we could actually say that affine geometry is sort of older than linear algebra itself because these sort of things were there since long time. And when I was saying that like different origin just mean a different perspective, but this actually how it pans out is like you could see. So here, let's say we have two observers. One is Alice. Uh, yes, just a second. Yeah, one is Alice, and then there is Bob. So both of them are trying to observe the same thing, but because they have different perspectives. So let's say the vector which defines D in Bob's perspective is W, and then vector which defines D in the Alice's perspective is V. And same for the point C, like it's the vector which defines it in Bob's perspective is A, and then in Alice's perspective is U. And when both of them try to add the vectors defining the point D and C, Bob gets this E vector and then Alice gets this B vector, right? So it basically seems like the same transformation in their perspective um, coordinate system gave them different result, but when we think about it, the different even though there are different perspective, but the different perspective are preserved are related by the translation. So Alice and Bob's origin are like there is this translation in their point of view, and then we could see the same translation in the output as well for their results. Yeah. So yes. So let's first discuss like what linear maps are. Then we'll maybe try to make sense of this part by adding translation to the linear maps. So what linear maps does is that let's say we have this unit rectangular region, and we could apply some linear map to it, and maybe like it will rotate that region by some angle, or maybe it could stretch that region as well, maybe something like this. Yeah. But let's say if you want to translate this, we cannot do that using a linear map, right? Like so if we basically want to do this transformation where this unit square region is translated to some another area where the dimensions are preserved, but like it is just shifted or maybe sort of teleported to that point. So that is what the translation is. And this translation is allowed in a affine space. And this sort of translation plus the what linear map does is carried out by the affine map. And how can we define such affine map is that so in this particular example, you could see like both of the regions are same in the measurement sort of term, like they are not rotated or skewed, but they are just translated, right? So if I want to represent the transformation, what I could say is that let's say I have this x and y vector x and y giving the position of the points, and then maybe some linear map which will give the rotation and then the scaling, which would be then like, if, or our case, it's an identity because there is no rotation and all. But there is some translation which we could define by an addition here. So as we could see, like the points are getting added by 2. So 2 and 2. So this basically comes out like, this matrix. So it's like x plus 2 and then y plus 2. And if you think about it, it is actually equivalent to writing it like this. Maybe the translation term comes here and then to actually when we consider about writing our x and y, we can just write a constant one here, right? And this will also give us the same result. But how can we interpret this, right? Even though there is this linear map, which is doing the rotation and the stretching and all, and there is this column which is basically doing the translation. So if we see at our variable vector, you could see we have basically added a dimension here, right? And what does this dimension mean is that we are trying to sort of interpreting this in a three-dimension space where the output is actually in the two-dimension space, and in the third dimension space we are trying to fix the z coordinate to 1, right? So we could actually extend our transformation in a such a way that, let's say, 1 0 2 0 1 2 and maybe 0 0 1. So if we partition this in this sort of way, so you could see this is our linear map in the 2D. Then this is our translation, and let's just think of this fourth row as let's just keep it as it is for now. You'll get to know what does that mean exactly. And when we see this transformation now, that you will realize it's basically a linear map in three dimension, right? But how would that work if it is in a linear map in three dimension? So let's see that. So here you could see, right? So there is this cube with each side having unit dimension, and then there is this green plane which is like at z equals to 1, because that is how we fixed our coordinate in the previous step as well. And when we do some shearing in this particular direction, we could see that the intersection of this particular cube, or maybe this solid now, with this plane basically shifts or translates to another point, which actually, if you look from the top, it actually looks like, it has translated. And we basically did not change anything apart from that. So I think let's visualize it. It will give you a better understanding. Yeah. So you could see in this particular illustration, we have this cube which has a unit unit sideline, and which is basically defined by unit vector along XYZ axis. And there is this linear map which defines the translation of it. So you could see, like, when I do this sort of translation where the cube is sort of squeezed now, so you could see like there is this linear translation metric which is changing. And on the plane as well, you could see this particular not translation, transformation is given out by this matrix. But when we change this z point in such a way that the top, which is showing the face of the cube, is now seems to be translated in this particular plane. So basically, what we are seeing here is that by doing some sort of linear transformation in a 3D space, we are getting a translation, effective translation in 2D space. So that is how we are, denoting the matrix. And obviously, the third row here, which is showing, is that, like, keeping the transformation constant in the third dimension apart from this particular plane. So yeah, so there are like particularly good. This is particularly good thing given that we are representing our affine map transformation map as a square matrix, and so because it is a square matrix, that means it's a linear map, and we could then basically do all the linear algebra stuff which we actually uh, have on this linear map to get the eigenvalues and then maybe inverses and everything. So yeah, that was a cool perspective to look at. So thank you.